Okay, I'm grateful to organize this. I hope the scope of my talk corresponds to the title of conference. So growth already is in the title, substitution also, words will appear. So here is part of the plan. I have 45 slides for 45 minutes. So basically, it's about connection between groups, substitutions, systems, automatically generated sequences and groups, and Schrodinger operators. Okay, so this is second part of my talk. Let us begin with representations and spectra. So let G be a countable or even finitely generated group, and rho arbitrary unitary representation in Hilbert space H. Take element of a group algebra C of G, say C over complex numbers or over real numbers, in fact. And then we are interested in the spectrum of corresponding operators. So we apply, we take unitary representation, apply to M, to element of a group algebra, which is just finite linear combination of elements of a group with coefficients, complex or real coefficients, and then when applying representation, we get operator. So we are interested in the study of operators that arise in this way, and general question, what is a spectrum, what are spectral measures, another spectral invariance, relations between these things. So the number of topics that can be reduced to this type of question is enormous, and many great problems of mathematics wait to be solved, and the corresponding questions are related to questions of this type. Okay, so I don't know where it is better to stay, on podium or here is okay? Huh? On podium is better? No, I don't trust you. Okay, so G is a group, finitely generated group, generated by this system of generators. One can take just average sum of generators. So we take the sum of all generators in S and inverses and normalize this, or we can use any weights, any coefficients. So this is just an arbitrary form, a general form of element in a group algebra in general. Or more specifically, these weights can be taken probabilities. So in this case, it's kind of a distribution of the set of generators and inverses. And then this, of course, is related to consideration of random walk, to topic like casting criterion of amenability, and so on. Now, what kind of representations usually arise? First of all, regular representation in A2 on a group. A more general type is quasi-regular representations when you have a group G, subgroup H, not necessarily normal, and you consider just action of elements of a group G on cosets, and you get permutational representation, which is called also quasi-regular representation, and this is a notation for this type of representations. Next type I call Koopman representation. Given an action of a group on a, say, probability measure space, X mu invariant or quasi-invariant probability measures, then you can associate a unitary representation pi, which is action of which is given by this formula. Only I observe that this G element G, group element G, is missed in this formula. So this is Radon-Nikodym derivative, which is 1 when measure mu is invariant. So it's action on a function f from L2 just by shifts in case of invariant measure. And the most complicated maybe a type of representations that will play a small role in this talk, but still is so-called groupoid representation kappa. So you have group action, group is countable, and even finitely generated, you consider corresponding equivalence relation. So subset R in the direct product of two copies of the space X on which group X, and this equivalence relation is given just by partition on orbits. Then you consider measure nu, which is roughly speaking a product of a measure mu on X and counting measure in each leaf. And so now functions are like functions in two variables, functions of in A2 on this equivalence relation R, they are function on two variables, but you act only on first argument or on second argument. And this is what is called a groupoid representation. Now, spectra of graphs. So given a graph, say M regular graph with set of vertices V and set of edges E, one can consider a Markov operator of averaging. You take the sum of values of function f for all neighbors y of x and normalize. So this is a Markov operator related with simple random walk on a group. Identity minus m is considered as discrete Laplacian. But more generally, again, you can put weights. You can associate with each edge a weight, certain number, and then consider corresponding operator, which kind of generalized Markov operator. Yeah, where interaction along edges correspond to weights of these edges. And then these examples fits in previous schemes given by a model of unitary representation, just because Markov operator on Schreier graph corresponds to quasi-regular representation. So what Schreier graph? We have a group, a subgroup H, and a system of generators, and set of vertices is just set of cosets, and two cosets are joined by H if multiplication of one coset by generator gives another coset. So this exactly corresponds to taking quasi-regular representation, and the element of group algebra of this sort, sum of generators normalized. And a general problem is to understand how spectrum of this type of operator depends on generating set S, and how spectrum of generalized Markov operator, when we use weights, depends on weights. So we keep a system of generators fixed, but change weights, and how spectrum may depend on weights. Very little is known. But here is an example. Our favorite Lamplighter group, which already was mentioned today several times. Two system generators, one standard system, when you take A, just generator of group of order 2, B, generator of infinite cyclic group. Another not quite standard, you replace A by product AEB, so BC. So the fact is that this generators BC just corresponds to the model when L is presented as a group generated by this two-state Milli automaton. And the fact is that with respect to the second, with respect to the second system of generators, the group, or Kelly graph of the group, has poor point spectrum. This is a result of Andrzej Żuk and me of 2002, which was later used together with Linnell and Schick to answer one question of Attia, namely to show existence, to construct a 7-dimensional manifold with non-integer L2 Bethe number. And the recent result, due to Grabowski and Virach, is that with respect to the first system of generators, spectrum is continuous. So no eigenvalues. Poor point spectrum means that there are many eigenvalues, and corresponding eigenfunctions constitute like basis in this case in L2, while in continuous spectrum no atoms at all, and even it's continuous singular spectrum. And so this is related to the kind of related to the first general question. This slide was missed, but maybe that's good. To this part of general problem and to second part, how spectrum depends on weight, the answer is given by this fact, which later will be given explained in much more details due to Daniel Lenz, Tatiana Nemedaya, and me, and it's reasoned that a spectrum Schreier graph may drastically be changed if you change weights of generators. It will be more precisely formulated in theorem 2. Now, a group that was mentioned in Alex Humbert talk, group of intermediate growth, I denote it by G star, is a group generated by 4 involutions. Originally, it was defined as a group acting on an interval by Lebesgue measure preserving transformation, but now a more modern point of view is to view it as a group generated by a certain 5-state automaton acting on a binary rooted tree in some similar way. These are kind of recursion, Vries recursion or whatever, showing that B, for instance, fixes vertices of the first level, and projection to the left subtree is A, while to the right subtree is C, and so on. So this is a group of intermediate growth, intermediate between polynomial and exponential. Appeared as the first example of such a group. And it acts not only on this binary rooted tree by automorphism, so preserving each level root is a fixed point. Each level is invariant set, and it acts also in the boundary of the tree, which is homomorphic to a Cantor set, important tool in Matsut talk. On the boundary, it acts by homeomorphism. On the tree, it acts by automorphism. So what is important for our talk that it can be given by many definitions, by many ways, and very nice definition of this group was formed by I.Lysenok. So group was discovered in 1980, while 5 years later, I.Lysenok, he proved that this group can be given by this presentation. So we have 4 generators. Certain, I miss here one relator, BCD, product BCD equal 1. So BCD commute and together with identity element constitute Klein, famous for order 4 Klein group, which also play some role in talk of Jeremy, second talk of today. But group is not finitely presented, and to get presentation, we use these two we take these 2 relators, AD to the power 4 and this one, and apply powers of this substitution. So I call it Lysenok substitution in the title, and you have iterate this infinitely many times, and you get presentation of this group. And this is minimal presentation in the sense that none of relators can be deleted without changing the group. It was not proved by Lysenok, later was proved by me. And this presentation gave kind of a direction in study of group presentation. Now they're called L presentation or endomorphic presentation, and many branch groups, groups of branch or weakly branch type belong to this class of groups that can be given by finitely many relators, and application of powers of substitution, of several substitution can be included. So this substitution will play a crucial role in future.
It's not in endomorphism, no? C gives endomorphism or not?
It gives endomorphism, but not automorphism.
It induces endomorphism.
Yeah, this sigma induces endomorphism of this group. So maps a group isomorphically onto certain subgroup, but of infinite index. Injective, yeah, but image is of infinite index, and in fact this group doesn't contain subgroup of finite index isomorphic to itself. Yeah, but that's a different story. And this is non-primitive. So in theory of substitutions, substitutional dynamical system, important role belongs to primitive substitution. So this is not primitive substitution because B, C, D just are cyclically permuted. When we iterate, B goes to D, D to C, C goes back to B, not primitive. A few words about actions in general, about actions on rooted trees. So if you have, in general, faithful action on so-called spherically homogeneous rooted tree, but just view rooted binary tree or rooted ternary tree, regular rooted tree, then as I told, group acts on the boundary of the tree. And this is topological dynamical system, actions by homeomorphism. Or one can consider a uniform measure on the boundary, uniform Bernoulli, uniform probability measure. So in case of binary tree, it is a half-half Bernoulli measure. And it is invariant with respect to the action of the full group of automorphism. So in particular, for any group acting on a rooted tree, it's invariant. So we get metric dynamical system, group acts on the boundary by measure preserving, probability measure preserving transformation. Yeah, mu is invariant. So here is like, okay, tree and some point of the boundary, Xi and the UN, let it be a vertex of level n, which belongs to this tree. Here is information about ergodicity, when this action is ergodic, if and only if it is level transitive on the tree. So transitive on each level of the tree. And this is equivalent to minimality of the action on the boundary. Each orbit is dense, and this is equivalent to unique ergodicity. There is only one invariant measure, and this fact holds for any group acting on spherically homogeneous rooted tree. So very general fact observed in my paper with Nekrashevich and Sushansky 2000. Now, the following proposition, now this is a joint work. I don't know why my name appears here the first, sorry. Laurent, okay, Laurent Bartholdi, 2000. So if you take any element of group algebra and consider Koopman representation, take Koopman representation, associated with this dynamical system, group acts on the boundary by measure mu preserving transformation. Then a spectrum of operator given by Koopman representation coincides with the closure of union of spectra of representations rho n. Perhaps I skipped some slide. Let me. This is very fast. Yeah. I told to Kate that should be another pointer. Okay, but this helped me to run quickly, even quicker than I was expecting. Yeah, so notations. Because each level is invariant set, so we can, with each level n, Vn is set of vertices of level n, we can associate permutational representation. So it's finite dimensional permutational representation. I denote it rho n. Yeah, and gamma n is just graph of action on a level n. So vertices of level n are vertices of graph, and two graphs are joined by an H if you can get one vertex from another by action of a generator. Now, if you take a point of the boundary xi, then you can consider orbit, g xi orbit of this point. Now, usually it's infinite orbit. I assume that the group is infinite. You take L2. But still, group X by permutation on its orbital, so you can consider permutational representation in A2, and this representation is nothing else just but quasi-regular representation, lambda g over h, where h is just stabilizer of the point xi. And infinite graph gamma xi is a limit of finite graphs, but a limit as marked graphs. So together with the graph, we consider initial point, gamma xi xi, gamma n un. Remember, un was a point on level n which belongs to path psi. So now we have approximation of infinite graph by a sequence of finite graph, which naturally converge to this graph. And so this proposition tells that this approximation give contribution to the spectral business. Namely, now if you take any element of group algebra and apply Koopman representation, you get operator in L2 on the boundary. Spectrum of this operator is spectrum closure of the union of spectra of finite dimensional representations. So we apply rho n representation corresponding to level n to element of group algebra. In fact, each next spectrum contains previous one. So here we have just increasing sequence of finite sets, but we have take closure of this. Okay, so this is one statement, and another is that for every point of the boundary, now if you take rho c, quasi-regular representation associated with point of the boundary, then spectrum of such operator is contained in the spectrum of Koopman representation. But if graph is amenable, in this case, here we have equality. So, okay, so here we have a result about relation of spectra for different representations, but in situation when we have action of a group.
It depends on T, so you still have a profiling system of groups.
Depends on
how much it depends on T, or just have given
on a tree? On tree?
Yeah. You give a profiling power, the general profiling powers.
It depends, first of all, how group acts on the tree. Because the same group can act on different trees, and in general, spectrum will change very much. Yeah.
If this result of this formula is so for all profiling towers, the existence of some finite things go to the limit, you act on this compact space, you use line measure, all this makes sense. Even the same result is true.
So it depends. It depends, but it depends. Yeah. For instance, in such a way, usually we get just a part of spectrum of regular representation. So if you want to get a spectrum of regular representation, really you must go through all subgroups of finite index. While here we consider only some special sequence of subgroups of finite index. So you get not all spectrum for regular representation. Okay. So in particular, if this gamma xi are amenable graphs for all points of the boundary, in particular if a group is amenable, then the spectrum of Schreier graphs, or graphs gamma xi, I forgot if I told, so the same like Schreier graph for action on orbit. This spectrum of this graph doesn't depend on the point, and just coincide with the spectrum of Koopman representation. Now I formulate very recent result, joint result with Artem.co. Now consider arbitrary action of a group G, countable group, on probability measure space X mu. But action should be ergodic, measure preserving. Now let pi be Koopman representation, kappa as before groupoid representation. Then statement is that for any element of group algebra, spectrum of Koopman representation contains spectrum of quasi-regular representation, which coincide with the spectrum of groupoid representation. But this we claim for almost all x.
What is subgroup? This quasi-regular means it is subgroup.
We take point x of space x, and rho x is just a representation corresponding of action of group on orbit of this point. So previously it was rho xi, xi was point of the boundary. Now rho x, x point of now x X point of space on which group X. So in comparison with previous statement, with this statement, here we claim that for all points of the boundary we have something. This inclusion holds for all xi, for instance. Now we claim that almost sure, this inclusion holds almost sure. So weaker, but now we don't assume group X on the boundary of the tree, but we consider general ergodic actions.
So again, in the simplest case, we mean the spectrum, if action is free, yeah? It said the spectrum of the regular representation contains the spectrum of this Cook representation, yeah? Because the relation keep forgetting who is who.
Yeah, if action is free, then PM is Koopman. Yeah, PM is Koopman. If action is free, yeah, it's Kelly graph, basically Kelly graph, and we claim the spectrum of Kelly graph coincides with spectrum of groupoid and is contained spectrum of.
For every measure or for every element, yeah.
For every element of group algebra. M element of group algebra.
G is the Grigorchuk group.
No, arbitrary countable group.
It's always contained in the regular representation.
Yeah, and okay, I included second part, but I have second part, but let me tell that maybe this is work in progress. So recently we got a proof, but maybe it is not 100% check. But it seems to me we are able to prove that if action is hyperfinite, so orbits are, partition is a hyperfinite, then we have equality of spectrum of Koopman representation coincide with spectrum of groupoid representation.
But spectrum in general is not simple, there are multiple spectra of how that. It's a spectrum multiplicity don't count.
About multiplicity, no statements. No statements. Okay, now let's go back to the group of intermediate growths. To the group of G stars that I denoted. And now we take an element which is just linear combination of generators, A, B, C, D. So coefficients are denoted T, U, V, W, some real numbers, which play a role of weights. Now, so group X on binary rooted tree, there is some special point, 1 infinity, the rightmost path, which plays some special role, and its orbit, points in the orbit. In fact, partition in this case for action of this group on the boundary rooted tree is so-called coffinality partitions. 2 points are in the same orbit if starting from some moment they are the same. And okay. So gamma xi is point of the boundary, gamma xi Schreier graph, m xi corresponding Markov operator in L2 on this orbit, given by these weights. So this is a picture how Schreier graph of action looks for fast free levels. I don't know, it is in color, maybe not very well visible, but still. So this figure was drawn by Laurent Bartholdi 16 years ago. So when you watch, it looks like crazy action. But if you look like more carefully, then you understand that, okay, for first level, clear, second level can be drawn gamma 2 second graph as this one, so it becomes something much nicer. Only vertices now are in strange order. For instance, for that level we have 1, 1, 0, 0, 1, 0, 0, 0. So the leftmost vertex appear here, The right modes 1, 1, 1 is on the right. Okay, nice pictures. Now what about infinite graphs? Here, in fact, here graph is drawn for this special point, for one infinity, and it is one-ended. There is one end is on the right. Yeah, so this is a kind of border. For other points, for points not in the orbit of one infinity, you have move like picture extend to the left. Graph becomes two-ended. Without labels, this is very simple graph. It's kind of a two-periodic graph. So if you are interested in spectrum of Markov operator of simple random walk, it's a very easy exercise to find spectrum for simple random walk when all weights are equal. Or even, so brown or red, I don't know, it corresponds to generator A. And other colors, blue, green, and yellow, corresponds to BCD. So if weights of BCD are the same, this picture, colored graph becomes two-periodic. And no problem how to compute spectrum. Use block theory or just give exercise to undergraduate student. But with labels, it becomes much more, in fact, complicated. And at that time, with Laurent, also we realized that this sequence of graphs and this infinite graph is sequence of graphs that can be given by graph substitution. But now we know that this is a situation when people pronounce these magic words a periodic order. Don't ask me what it means, but okay. Who knows? I hope that he recognizes there is a periodic order in labeling of this structure, and for one-sided, one-ended version, and for two-ended version. And so what is a second theorem, which was already mentioned? So in case when weights for BCD are the same, then spectrum of course weighted Markov operator is union of two intervals. And the absolute spectral measure is absolutely continuous with respect to Lebesgue measure. And in fact, as I told, this is pretty easy to show, but I will give more comment slightly later on this part of theorem. And the second part is a recent result with Lenz Tatiana again. Then if equalities doesn't hold, so at least one of weights for BCD is different from other, in this case, spectrum of weighted Markov operator is a Cantor set of Lebesgue measure 0. So this means the change of weights of generators may lead to the catastrophic change of the nature of the spectrum of Schreier graph. Okay, I have how many minutes? 10 minutes to explain how this comes, and 4 minutes I will spend to part A, which is trivial, as I told, but with Laurent, we decided to solve it in a non-trivial way. And we, it seems to me, invented a certain method that preparing this talk, I came to conclusion could be called S-cube. Spectral problem method, which stands for self-similarity and Schur. And this method, roughly, I give very rough description of this method, because in this situation, yeah, we could use block theory or whatever, but it is applicable in many other situations, much less trivial. And the idea consists of including operator in certain family of operators depending on some set of parameters. Usually we assume that these parameters take value in a certain finite dimensional space. So M is a particular case of a family of operator MP bar, where P bar point in RQ. For some Q, for some natural number Q, so for some particular value P0, if we substitute, we get our operator M. And so we are interested in those E, this spectral parameter, which is usually denoted lambda, but lambda in my talk is a regular representation. So we are interested in set of E for which M minus E identity is not invertible. But using self-similarity and the operations that people in this order, what order? A periodic order called maybe telescoping. So we replace M by matrix, matrix of certain size, and then apply Schur complement. And roughly speaking, Schur complement is a very old idea that if you have a matrix, operator matrix with A, B, C, D operators in classical situation, it was matrices, finite dimensional situation, and if the kernel is invertible, then such matrix is invertible if and only if this expression is invertible, and this is called a Schur complement corresponding to this kernel. And similarly, you can define a Schur complement corresponding to another kernel. And then using this, you get a certain map, multidimensional rational map. Now from RQ plus 1 to RQ plus 1, where Q was before, so one dimension higher, so that the set sigma, which is the set of values of pairs parameter space plus spectral parameter, when this operator, this difference is not invertible, so kind of joint spectrum. This set is F invariant, invariant set for this multidimensional rational map. And so the problem, if you have this F, the problem is to identify this finite dimensional, this invariant subset, and then intersect it. So intersect it by prime given by this equation, and intersection will be spectrum of original operator. So this was how part A was solved. In this case, Schur complement give this two-dimensional map, and set sigma is a blue set on this picture, and the spectrum of operators that interest us was the crossing of this set by this vertical line when one parameter is equal to minus 1, so it's a union of two intervals. If you apply Schur complement to another kernel, you get this another rational map. And if you want to solve a problem for parameters, for different parameters, T, U, V, W, so the 4 parameters plus spectral parameter, you get five-dimensional space of parameters. And if you apply a Schur complement, you get this nice map, which was found by Nekrashevich and me, basically by Nekrashevich, who managed even to factorize denominators in these crazy products. But what is corresponding invariant subset for this map? It's Pecker's problem is problem not for this century. So like in 2007, when with Volodya we got this map, we were puzzled. Okay, can one say something about invariant subsets of this map? No idea. So at that moment, no idea what is the spectrum. Here is one more interesting example. It's a so-called Hanoi Tower group H3, group given by this free-state automaton of a ternary alphabet. This is a Schreier graph corresponding to level 3. I don't write what is a map in this case, but set sigma is a union of hyperbolas, and crossing by vertical line gives you a Cantor set in this case. So this is one of the examples when this method, S-cube method works. And so we have a number of examples when spectrum can be explicitly computed. Okay, now let's go to I.Lysenok substitution. I slightly modify it. Instead A, B, C, D, I use A, X, Y, Z. This is basically I.Lysenok substitution, but written slightly differently. Now we consider space of two-sided infinite sequences over this alphabet. T is a shift in this space, and because image of A is AXA, which contains A as a prefix, you can start iterate, apply powers apply powers of substitution tau, and you get sequence, increasing sequence of weights, which next contains previous as prefix. You take inductive limit. Eta is infinite one-sided sequence at fixed point of this substitution. Then you move it to left to get a subset omega tau, space of infinite two-sided infinite sequences, and it is T-invariant subset in omega, and this is substitution dynamical system generated by eta, in fact, by original substitution tau, by I.Lysenok substitution tau. And this is a big part of mathematics, a study of substitutional dynamical system given by substitution. Usually in this investigation, substitution is assumed to be primitive, and sometimes even satisfy certain extra conditions. Here we are in a situation where the substitution is not primitive. Okay, so theorem 3, again due to Daniel, Tatiana, and me, tells us that this system has the following properties. Doesn't contain 4 powers, but contains 3 plus epsilon, where epsilon any number between 0 and 1 powers. So this fixed point is infinite weight. It doesn't contain cube of non-empty, 4 power of non-empty weight, but contains 3 plus almost full period. And this is important for some spectral things in the results that we have. Now the system is linearly repetitive, so-called linearly repetitive. Let me not define this. Hence, it is minimal and uniquely ergodic. The complexity function, number of weights which appear as subweights in infinite sequences, grow linearly. System has poor point spectrum, and any measurable eigenvalue is continuous eigenvalue and belongs to this set, to this group of roots of 1. The binary odometry is the so-called maximal equicontinuous factor of this dynamical system. And the group of intermediate growths is the subgroup of the topological full group generated by this subshift. So result of Kate and Monod was already mentioned. That topological full groups and their commutator, which are finitely generated simple groups. By the way, the names of Giordano, Putnam, Skau, Bezugli, Medinets, perhaps were not pronounced yet, so who contributed a lot in study of topological full groups. With Kosti Medinets, we added a little bit. So these groups really and their commutator subgroup have interesting properties. For instance, they are locally embeddable into finite groups. So Sophic, for instance, they are product of 2 locally finite groups. So finitely generated infinite simple group can be presented as a product of 2 locally finite groups. They act totally non-freely on the on space. So in particular, this implies that there is a ergodic continuous invariant random subgroups, and so on. I understood hint. Yeah, theorem 3 was mentioned. So perhaps this is the first example when we have a substitution such that a group of intermediate growths embeds into full topological group of it. But here, of course, I cannot not mention Nicolas Bon results. So in fact, our system group X on the boundary of the tree, it is covered by so-called Schreier dynamical system studied by Vorobets, which is covered by action of group G star on this space omega tau. And Nicolas Bon, he showed that here, in this situation, in this space X, which is space of Schreier graphs, there is minimal homomorphism such that the group of intermediate growths G star embeds in topological full group associated with this homomorphism, while here it cannot be. For this action, there is no such a homomorphism. And the last, okay, I had no, yeah, this is the last what I want have to say. So there is this aperiodic order, which we viewed on picture for graphs. It just makes, in fact, a relation with theory of random Schrodinger-Jacoby operator, and all proved main result about this substitution, and known result in theory of random Schrodinger operator allow us like to conclude that for each set of parameters T, for each set of parameters, we can find point in our substitutional system so that corresponding Jacoby, Schrodinger-Jacoby operator is unitary equivalent to the weighted Laplacian. And so what is known about Schrodinger-Jacoby operator can be translated to this operator. In particular, we can provide proof of part B of theorem 2. Thank you for attention.
Is there any question? Okay, if not, let us thank all the speakers of this afternoon.